So thank you very much for that warm introduction, Jan, and thank you everyone for coming. Welcome. It's a real pleasure to be speaking here this evening. Before I start, can I just get a show of hands? How many of you have heard of Chat GPT? As expected, everyone. How many of you know what it is and how it works? So about 50% less than people who have heard of it. And that's pretty much the state of affairs right now. And this is already a pretty informed audience, I would imagine, given the nature of the audience. But the technology has really kind of, as Peter was saying, it's really making waves, and there is real cause for being inspired by what's happening, but also real cause for being worried about what's happening. So this talk is really going to try and explain kind of where this technology comes from and how it works in as simple a manner as possible. And there are people in the audience who already know machine learning and AI way, way better than I will ever understand. And for them, this talk might be very basic, but I'm actually aiming this talk at people who have little knowledge of this subject. So there might be things here that might seem very obvious to some of you. So please bear with me while I talk about these things in a way that all of us then end up on the same page, so that we can then talk about sort of the concerns and other issues that this technology is raising. But before I begin, I want to talk about a little bit about an idea that comes from psychology, and it's something called theory of mind. And the reason why I'm going to talk about this will become clear as we start talking about Chat GPT. And it's this idea called theory of mind. And this is something where each one of us as a human being has the ability. So when we see another person and look at their face, and if they are smiling or frowning, we can immediately kind of infer what is happening in their minds. We kind of make some inference about their state of mind. Are they happy to see us, or they're upset at seeing us? Basically, we use cues from their face, from their body language, to kind of estimate what might be happening inside their mind. So we have a theory about what might be happening in someone else's mind. So this ability that we have as human beings is called theory of mind. And the question, and I'll link this to ChatGPT in a moment, but this is a theory, interestingly, as adults, most of us, not most of us, all of us, will have this ability. It's not even something cognitive, it's just something we have. But what is amazing about the theory of mind is that it is a ability in humans that only starts appearing in children around the age of 3 or 4. So if you were younger than 3 or 4 years of age, you will not have this ability. And there's a very simple test to try and see if somebody has this capability, and particularly very young children. And it's something called the Sally-Ann test. And I'll just talk to you about this a little bit, because this leads into a question that I then posed for ChatGPT to see if it has the ability, or it has kind of pretenses of being capable of similar reasoning. So here's the test that you can do with a child. So there are two people, Sally and Anne, and they're in a room. Each one has a basket with a lid. Sally hides a marble in her basket, closes the lid, and then leaves the room. And when Sally is out of the room, Anne takes the marble from Sally's basket and puts it into her basket and then closes the lids, right? And then Sally comes back into the room. And the question for whoever is being asked this question is, where will Sally look for the marble? Remember, Sally was not in the room when the marbles were switched. And now the baskets are closed so that there's no way to tell where the marble is. So where will Sally look for the marble? All of us will say, well, I know that the marble is in Anne's basket, but Sally doesn't know that. So Sally is going to look for wherever she put it. And essentially we are inferring, we are theorizing about what might be in Sally's mind, right? And this ability is called theory of mind. Interestingly, a 2-year-old child will say, I know that the marble is in Anne's basket, so Sally will look in Anne's basket. So the 2-year-old child, 3-year-old child also probably, will not be able to pass this test, right? So they will not be able to attribute Sally's state of mind as being different than their own, right? They understand where the marble is. They think that's exactly what Sally will also be thinking, but in this case, Sally is not thinking that. So my interest in this comes because I've been writing a lot about issues in neuroscience and psychology, and so I wanted to test if Chat GPT has theory of mind, right? So I'm just going to show you a question I asked it, and one of the things about Chat GPT, and this will become clear, I haven't told you anything about what this thing is, what Chat GPT is, how you test it, etc. But let's say for the moment that it is a piece of software that you can ask a question in natural language, in this case English, and it will then reply back with its answer. Let's just for now assume that's what it's doing. And this is a question, and you have to come up with questions that it hasn't actually seen in the data that it has been trained on. So if you just took a standard Sally-Ann test, there are lots and lots of papers that have been written about it. There's internet is full of these examples. So you don't know whether ChatGPT is just regurgitating what it has already seen, or is it actually doing some kind of thinking. And I'm going to be using these scare quotes all the time when I say ChatGPT is doing reasoning or thinking, because it is not at all obvious at some level what is happening. So this is the question. Alice and Bob are in a room together. There's a table with 2 drawers. Alice takes off her reading glasses and keeps them in the left side drawer. If Alice wears the wrong glasses and reads, then she gets a severe headache the next day. Keep this in mind. I'm telling ChatGPT this, not you. And the question continues. Now Alice leaves the room. When she's outside, Bob removes her glasses and puts them in the right side drawer. In the left side drawer, he puts a pair of glasses that look exactly like Alice's but have the wrong power. He closes both drawers, so there's no way to tell that he switched Alice's glasses. Alice then comes back, takes her glasses, and starts reading. How will she feel the next day? Think carefully and answer. Again, that think carefully and answer is meant for ChatGPT, right? Now, again, for all of us, the answer is obvious, right? Alice has, well, I'll show you what ChatGPT said. That's more interesting than answering it ourselves. This is what it says, right? Since Bob switched, this is verbatim from the transcript of a conversation I had with ChatGPT, okay? So since Bob switched Alice's reading glasses with a pair that looks identical but has the wrong power, Alice will unknowingly, and that underlining and italics is mine, Alice will unknowingly use the incorrect glasses when she starts reading. As mentioned, if Alice wears the wrong glasses and reads, she gets a severe headache the next day. Therefore, Alice will have a severe headache the next day as a result of using the wrong glasses. This was its answer, right? I continued asking the question further. Why will Alice unknowingly use the incorrect glasses? This is the response. Alice will unknowingly use the incorrect glasses because Bob switched her reading glasses with another pair that looks exactly like hers, but has the wrong power. When Alice returns to the room, she is not aware of the switch and assumes that the glasses she picks up from the left side drawer are her own. Since both pairs of glasses look identical, she has no way of knowing or realizing that the glasses she's using are not the ones she initially placed in the drawer. As a result, she uses the incorrect glasses without knowing it. This is ChatGPT's response. Now, if you just read this, and if you did not know anything about how the technology works, would you say that ChatGPT is reasoning? Would you say, so who thinks it's reasoning just based on this information? Yeah, pretty much everyone is beginning to say that. That's interesting. Would you say that it's demonstrating theory of mind? The ability, like if you look at those underlined words, the italicized words, she is not aware. She assumes. She has no way of realizing. Those are phrases that are suggestive of somebody knowing what's happening in somebody else's mind, right? It's able to kind of model what Alice might be thinking, right? So given this, would you say ChatGPT has theory of mind? How many? Just based on this, without any, so a fair number of you think it has. Well, we'll come to that. So this was this basically leads us to talking about what ChatGPT is and why we have come to this point. And we're going to take a really accelerated course through the history of machine learning, starting with something that might have happened in the late 1950s, then something that happened in the 1980s, and to now. Like, it'll be a really fast move through the decades. But what we just witnessed was an artificial intelligence interacting with us, right? But what is artificial intelligence? And these are very, very basic definitions that we can keep in mind. People will, especially the experts in the field, will kind of disagree on a lot of these issues, but here's a very general way of thinking about what AI might be. It's basically the ability of machines to perform tasks that typically require human intelligence, right? We just witnessed an example of that, where we asked ChatGPT something. You could have asked a 2-year-old child, a 5-year-old child, an adult, and we would have gotten back similar responses. And here was ChatGPT demonstrating an ability to answer a question that typically needed human intelligence. And why would you want to use AIs like that? Well, for things like pattern recognition, so systems that do face recognition, for instance, right? So those, faces are essentially patterns in images, and the ability to recognize faces, that's a kind of AI. Processing natural language, which is, we just saw ChatGPT do that. It basically responded to a question that was posed in English and responded back in English, right? So that is kind of the ability to process natural language, do speech recognition, things like that. Making decisions. Well, in this case, we did not see any decision being made, but let's say you use the output of ChatGPT to figure out whether Alice is going to need headache medicine the next day and take a decision to order the medicine from the pharmacy. That would be a decision that would be based on some output that ChatGPT produced. So that would be an example of how you could take something that the AI did in natural language, turn that into an action, and learning from experience. We haven't yet talked about that at all, but that's going to be the focus of the talk today. But machines that are able to learn from experience meaning encountering the environment and basically making sense of the environment and being able to sort of act upon that experience and kind of modify themselves based on that experience. So this is, in general, what AI is and what it can do. And of course, again, this is a very, very loose definition. If you just think about AI overall, there are broadly speaking, there are two broad categories of AI that exist. One is called symbolic AI, which is also kind of somewhat derogatorily called good old-fashioned AI, which used to be popular in the 80s and 90s, but has since fallen out of favor. We won't have time to get into that. Maybe in the Q&A, if somebody wants to talk about it, we can bring it up, but let's just keep that aside for now. The kind of AI that you're witnessing now, especially ChatGPT and these large language models, are what are called machine learning AIs. I mean, machine learning is basically machines that can learn about patterns that exist in data. So they see data and they are able to learn about the patterns that exist in the data and then use what they have learned in order to make predictions about new data that they haven't seen before. And then that can then be used to, do tasks, to make sense of things, to reason. All sorts of possibilities arise. But machine learning is basically at the heart of what's happening today. And you would have heard the phrase deep learning or deep neural networks, and that's a subset of machine learning. It's a kind of machine learning, and that's what we're going to talk about, right? So I'm going to take a very quick example to demonstrate to you what machine learning might be. Again, for people who know machine learning, this is going to be so silly and so basic, and I apologize in advance. But I put myself back a few years when I had no idea about this subject, and so I'm hoping that for those of us in that boat where we don't know anything, this would be helpful. So let's imagine we go to the fruit seller outside the main train station, right? And there's two baskets, one with apples and one with oranges, but there's no price on them. So there's no sticker saying this is how much an orange costs and this is how much an apple costs. You just pick up one apple and one orange, and the fruit seller says, okay, give me €3. Of course, These are very expensive oranges and apples. So you buy one apple and one orange, and the fruit seller says it costs you €3. Now you're trying to figure out, okay, well, how much is one orange and how much is one apple? The fruit seller doesn't tell you. All you have is this data that you bought one apple, one orange, and you paid €3. Is this enough information to tell us about what would be the cost of one apple or one orange? Obviously not, right? So you say, okay, I'm going to pick up 2 apples and 2 oranges, and now the fruit seller says, okay, give me €6. Again, you say, okay, this is obviously not enough information because this is exactly the same as the previous thing. You can multiply the first equation that you have by 2, and you end up with the second one, right? So it doesn't help you at all. So you do something else. You say, I'm going to take 2 oranges and 1 apple, and then the fruit seller says, okay, give me €4. Now you have enough information to discern what the cost of an orange should be and what the cost of an apple should be, right? And some of you will be able to do this in your head without any problem. Some of us will require a pencil and paper. Depending on our bent of mind, it might take a little bit of effort, but this is actually a fairly trivial thing to do. And with a little effort, mentally, or with a pen and paper, you can figure out that an orange costs €1 and an apple costs €2, right? So what we just did by figuring out the cost of an orange and the cost of an apple based on a little bit of data, right? We bought a certain number of apples and a certain number of oranges, and we looked at what the total cost was in a couple of different instances, and we used that to figure out what the cost of an orange and an apple individually is. What we just did was build a very simple model for ourselves in our minds, where we said, given number of oranges and given number of apples, I can calculate the total cost by multiplying the number of oranges by €1 and the number of apples by €2, and I get the total cost, right? This is what we did in our heads. I'm just going to move that equation into the model. So this is the model. We basically have the model as input receives the number of oranges and the number of apples, and inside the model is basically an equation that calculates the total cost, and it produces the output. We did that in our heads. That's what a machine learning model does. It basically figures out, you can write a piece of software that could do exactly this, and it would figure out, what about, I'm just going to replace the 1 and 0. So all I've done here is taken those one. So again, the next few slides are a bit nerdy and a bit geeky, and again, I apologize for this, but I think it's kind of necessary to get where we want to get to, right? And it's very straightforward. So I just replaced the 1 and 0, the two numbers, or 1 and 2, with W1 and W2. Just symbols representing the numbers that we just figured out. And inside the model is the equation that says W1 times 0 plus W2, or not 0, W1 times orange, the number of oranges, and W2 times the number of apples, right? And now it produces the total cost. Now, when you look at it this way, apparently there is a, let me see, there it is, okay. So when you look at what's happening here, what our model does, or what our mind did, was we actually figured out what the value for W1 and W2 should be, right? And based on the data that we had. And that's essentially, again, what a machine learning model does. It's kind of figuring out what these parameters must be in order for the entire thing to satisfy the data, the pattern that you saw in the data, right? So I'm just going to do a few more things. This might look more complicated than it needs to be, but again, we can't completely get away from this. All I'm doing here is replacing the number of oranges and the number of apples by two other symbols, x1 and x2, and w1, w2 remain the same, and the equation remains the same, except O is replaced by x1 and A is replaced by x2, and there's an output called y. All that has happened now is this has become more generic. It's not about apples and oranges. It can be any data, right? Where you have x1 and x2 on one side and the corresponding y on the other side. And if you have enough instances of these pairs of inputs and outputs, you can actually write an algorithm to figure out what W1 should be and what W2 should be, right? Basically, you're learning. No one has told you what W1 and W2 are, But you look at the data, somebody gives you examples of, here are pairs of x1 and x2 and the corresponding y, and you figure out what w1 and w2 should be. And essentially what we are doing, this is the only equation in the whole presentation. Oh, maybe there's one more, I forget. But basically all we have done is figured out a function, a transformation of somehow we take the input values of x1 and x2 and somehow transform that into y. We have learned what that function f is. In this case, the function f is very straightforward. It's a very simple w1 times x1 plus w2 times x2, right? That's all the function is. And we've learned, in this case, based on the data that we were given, in our case it was apples and oranges, it could be anything, we learned what those they're called weights, hence W1 and W2. And the weight simply means how much weight is the model giving to the input x1 versus how much weight it's giving to the input x2, right? So this is what we have just done, weirdly enough, is taken the very first basic step in understanding what a machine learning algorithm might be doing. It's essentially learning some way to transform the inputs to the output in the form of a function. It's learning, in our case, we learned a very precise function, but it could be an approximation of that function, and it does its best to learn that. And you could also do something very strange. For instance, if you went to that fruit seller and he said, oh, if you buy something that is less than 5 euros in total, you pay me nothing. Right? No fruit seller will do that. Let's assume this one will. And so you buy one orange and one apple and it's less than 5 euros, he says, okay, don't pay me anything, right? And then the moment the total cost exceeds 5 euros, he wants you to pay the amount that is over and above 5 euros. So if it's 50 cents or, say 1 euro over 5 euros, if the total cost is 6 euros, he'll say, pay me 1 euro. So there is a function that can be used to figure out that mapping. And if you saw enough instances of that, the fruit seller doing that, you could figure out what that function could be, right? So what we have just done is essentially created a model of something that's called an artificial neuron, right? I mean, there are, again, I'm simplifying this tremendously. And the reason why it's called an artificial neuron is because this is very loosely inspired by how biological neurons work. And you could make this model more complicated. You could have 4 inputs and more complicated equation and an output y. And again, as long as you have enough data on the input side that you know what the output should be, if you're given enough examples, you can figure out what this function should be or what the values of these parameters should be so that the input is then transformed into the output, right? And the reason why this is loosely inspired from a biological neuron is, well, here's a kind of caricature of a biological neuron. Biological neurons have a neuronal cell body. They have these projections called dendrites that bring in information into the cell body, and then there is an axon that's leaving the cell body that goes out to other neurons. And what's happening here, in a very simplistic way, is that if there is information coming in through the dendrites, the cell body is doing some computation. We don't know exactly what. It's doing some computation, and then based on whether the computation ends up in, let's say, a result that exceeds or doesn't exceed some threshold. Let's say if whatever computation it does, the result of that computation is below some threshold value, then there will be no signal coming out of the axon. But if the result of the computation exceeds that threshold value, you will end up with a signal going out on the axon. And this axon then connects to other dendrites from other neurons, and that's how biological neurons talk to each other, right? This is, again, a very simplistic caricature of a biological neuron. The example I was taking of a fruit seller who may not charge you as long as the total cost of the apples and oranges is less than 5 is an example of inputs coming in, and whatever computation you do, that sum doesn't exceed 5 euros and the output is 0. You don't pay anything. But the moment the cost exceeds 5 euros, there is a signal on the output side, right? So what we have here then is the machine learning model is, the artificial neuron that we just talked about, this one or this one. These are very, very simplified versions of the biological neuron. And the caricature of the biological neuron is itself a simplified model of what might be happening in biology actually, right? So once you have artificial neurons, you can start connecting them up. You can, these are all little artificial neurons. Each one is doing some calculation, and you have inputs here. This is just an example. It could be anything, but basically what you have here is the inputs are going to each one of the neurons, and these neurons are then producing an output, which is going to some other neuron, which is finally producing an output, right? So you can start constructing these networks. And what you're able to do as you construct these networks is you can start learning more and more complicated functions. What we saw with the apples and oranges example was a very simple function that was transforming the number of oranges and apples to the total cost. But in real life, that transformation can be extremely complicated, and the network has to learn what that transformation is. And it learns that as long as you have enough data to tell it how the input relates to the output, right? And you can build bigger and bigger networks. Here's what's called a deep neural network, where basically you have the inputs coming in. Notice now it goes from x1, x2, x3, and there's some indeterminate number of inputs here. It's gone up to xn, basically saying this is a large number. And similarly, there are a large number of neurons that are getting those inputs. Those things are now talking to neurons in another layer, and then those neurons are then telling, and I'm using the word neurons here without saying artificial neurons, but the implication is this is happening in software, not biology, right? And then you have an output neuron that's producing some output. So this thing is going to be capable of learning a transformation that is much more complicated than what we just saw as an example, right? And the reason why, when you hear the term deep neural networks, all it means is that there are layers of neurons that are sandwiched between the input layer and the output layer. If all you had was the input layer and the output layer, that is not a deep neural network. Here, the moment you have even one single layer of neurons between the input layer and the output layer, that technically classifies as a deep neural network. It can be deep in the sense that there can be one layer in between the input and output. There can be 100, there can be 200, doesn't matter. They're all deep neural networks. So how is this really used? And I want to take one example. This is all leading up to Chat GPT, just in case we've lost the thread here. So here's an example of something that computer scientists did in the late 80s. They used deep neural networks to solve this task of recognizing handwritten digits. So there's a data set that's available where, and why would you want to recognize handwritten digits? And the reason for this was in the US Postal Service wanted to automate the process of sorting mail. And of course, the best way to sort the mail is by looking at in the US it's called the zip code, but basically the postal code. And people write the postal code in all sorts of ways. They have all sorts of ways of, like if everyone is writing number 5, I bet each one of us will write it slightly differently. So you want some automated way of realizing what is the pattern that makes a 5, what is the pattern that makes a 9, what is the pattern that makes a 2, so that you can automate that process, right? So essentially, that data set that is used to train a machine to recognize digits is made of images like this. So I think this is a 3, I don't know. This is definitely 0, 4, but these are basically 28 pixels by 28 pixels images, grayscale images, which means that there are a total of 784 pixels that make up each image, right? And the task is, how do you train a neural network that we just saw an example of? How do you train it so that it can understand which pattern constitutes a 1, what pattern constitutes a 9, what constitutes a 3, and so on. And once it has learned that, then when you present it with data that it hasn't seen, like a new piece of mail comes in and the scanner scans it, presents a digit to the neural network, and it says, oh, that's a digit 3, right? How do you do that? And the way you would do that, again, very simply, is first of all, you have to take that image, which was a 28 pixel by 28 pixel image, and turn it into something that a machine can understand. And the way you would do it, 28 by 28 is 784 pixels. So you basically, line up those pixels as a long number that is 784 numbers long, right? Where each number represents the value of 1 pixel in the image. And it's a grayscale image, so the image can have a value from 0 to 255. It's either completely white or completely black or some shade of gray in between. So basically, x1, x2, x3, all the way to x784 are the values of the pixels of a single image, right? You present that to this network, and on the output side, notice instead of one neuron, I have here 10 neurons. So there is one neuron for each digit, 0, 1, 2, and 9. And the idea is that if you present the pixels of an image which, say, contains the number 4, or in this case, let's say number 2, then only the neuron that represents number 2 should produce an output saying, I've seen number 2, and all the others should remain quiet, right? And if you present the pixels of an image that has the number 9 in it, then hopefully the output neuron for number 9 specifically will fire, and all the others will remain quiet. But how do you teach it, right? So you've got this data set, let's say 50,000 images, where some human has looked at all those images and said, this is 0, this is 5, this is 9. And let's say you present an image that is the number 2 to this neural network, right? And then it has all these weights, all those W's that we saw earlier, right? Every connection has a weight associated with it, which is some W, W1, W2, W all, in this case, there'll be tens of thousands of W's. And the point is, based on those W's, each one of these neurons is going to do some calculation and propagate the result to the next one, the next one. Eventually, something will happen on the output side, right? Let's say that you present the number 2 on the input side, and instead of number 2 firing, number 9 fires. So obviously, it's made a mistake, right? It's made a mistake, and machine learning mathematicians have a way of quantifying the distance. Like so what it's made an error. You can quantify what that error is. So it should have said 2, instead it said 9. So it made some error. You take that error, and that error is basically being caused because the weights are wrong. Just like when we were doing apples and oranges, if we had chosen W1 equal to 0 and W2 equal to 4, we would have got the wrong answer in the beginning. And then we have to change the W1, W2 so that we get the correct value for the apples and oranges. Similarly here, based on the error that this network makes when you present an input, you calculate how much of an error it made, and then go and tweak these knobs. So think of these parameters as knobs that can be tweaked. And you tweak them ever so slightly, so that if you present the same number again to the network and look at what output it produces, now it will make an error that is slightly smaller than what it did before. So the error is slightly reduced. It's not yet got it perfectly. So, and then you have to keep giving it that number until, instead of firing 9 or 0 or 1, it finally fires the number 2. Right? So you're basically saying that the network has to minimize the error it makes, and what it's doing as you're going through the iteration, I'm just talking about one number here, right? It's adjusting all the W's that are associated with the network. So there might be tens of thousands in this particular network, and each one of those has to be adjusted a little bit, such that given the same number 2 over and over again, the loss that it makes, or the error that it makes, is taken away, and it finally does it correctly. But that was just one number. We have 50,000 other numbers in that data set. So you have to present each one of them and make sure that each of those numbers is classified correctly by this network. And by the time you're done iterating over those 50,000 images over and over again, you will end up with a set of W's for this large network. Like I said, it could be 10,000, 100,000 W's that will have values that are now capable of taking at least the data set that you were using for training. You could use, for all those images, it will produce hopefully the correct answer on the output side. It will make errors, and the idea is to minimize the errors that it makes. Now, so when you've done that, you actually have got a large neural network that is capable of recognizing digits. Now you scan another handwritten digit and turn it into a large number that is 784 digits long, all those 784 pixels, feed it through this network. It will produce a signal at 2 saying, oh, that's a number 2, or oh, it's a number 9, whatever. It could be anything. Again, it will make errors, but the idea is that you have trained it so that the errors that it makes have been minimized. So this was an example of how you would use a network. Oh, finally, Chat GPT. Okay. this brings us to, so when I talked about the very simple model, that was something that was happening in the 1950s with artificial neurons. We just talked of recognizing digits that happened in the 1980s, and now we're jumping all the way into the 2010s with large language models. So what is a large language model, which is what a Chat GPT is? A large language model is essentially this box inside which is a very, very, very large deep neural network. The exact ways in which it's connected, the exact ways in which the layers are organized, the exact way in which the connections are organized is actually not important for us to understand what is happening conceptually. Conceptually, what is happening is this box, I was going to say black box, it's actually, I should have turned this into a black box rather than a white box, but this is a black box which has, in the case of large language models, you have literally millions or hundreds of millions or billions or even hundreds of billions of parameters, those tunable knobs, those W's that I was talking about, right? In this case, you have literally hundreds of billions. At least Chat GPT has, I think, something like 200 billion. One version of it has about 175 billion W's that it needs to adjust. But why is it adjusting, and what is it adjusting, and what is it doing? Well, what it's doing is something like this. Let's say you had a sentence here. You knew what the whole sentence was. The sentence is the dog barked when it saw the, you know exactly what this word is because you have that input in hand, except what you do is you mask it. You basically blank it out. And you're asking your black box or your deep neural network to predict what that final word should be, what the next word in the sequence should be, right? And let's say it has randomly assigned values for all its parameters. We don't know what it is in the beginning. It's just some randomly assigned values, or maybe, so let's say that it produces this output, right? The dog barked when it saw the tailor, right? Now, we know what it should be. Let's say the actual word is cat, right? And we expect it to produce the word cat. Instead, it produces the word tailor. And when it produces the word tailor, mathematicians have a way of calculating so in mathematical space, cat is somewhere here in some very, very high dimensional space, and tailor is somewhere quite far away from it. And there's a large distance between the two, and that distance signifies the error that this thing is making when it makes a prediction. So it's got the prediction wrong. You calculate how wrong it is, and then based on the error it made, you go and adjust each one of those 100 billion, 200 billion, whatever the number might be, parameters, just tiny bit, very slightly. And then you feed it the same sentence again and see what it does. Maybe this time it will produce, instead of tailor, it might say when it saw the monkey, right? Now, here's what's happening in mathematical space. Here's cat in one corner of the mathematical space. Tailor was somewhere here. They're very unrelated, cat and tailor. Monkey, as it turns out, is slightly closer to cat than a tailor is. And so the error that the network has made in a mathematical way of thinking about words, I had to mention something else before, but basically, if it produces the word monkey, it has actually reduced the amount of error it made. And you keep doing this over and over again. Just tune those parameters for that one sentence, right? You keep tuning it till it produces the word cat, right? And when it produces the word cat, these tunable parameters, those 100, 200 billion of them, have been tweaked just right so that at least for that one sentence is able to predict the correct word. What I wanted to say before I started on this was just like we had to figure out how to turn an image into a number that a machine can recognize. We have to do something similar with words, right? And we don't need to go into this, but there are standard ways of turning this sentence into a set of numbers that the machine can understand, and then it will output us, again, numbers, and then we turn those numbers back into words. And it's because it's dealing in numbers, these numbers have locations in some very high dimensional space, and you can figure out how far away one is from another. So the number for cat is very far away from the number for tailor, and the number for monkey is actually closer to the number for cat than tailor is to cat. So you can keep reducing the error that the network makes. But what we did was just one sentence. Now imagine you take tens or hundreds of millions of pages of text from the internet, right? basically scrape everything that is there, that humans have put out as written language that's on the internet, and take every sentence that is there in every document, right? And start doing this. Take a sentence, blank out the last word, ask it to predict that word, right? And you keep doing this over and over again for every sentence, for every page that is there on the internet. And finally, for all of the text that's out there, if no matter what you give to the network, if it satisfactorily, I say satisfactorily because it'll never be absolutely correct, but to the best possible extent, predict the word that was missing, what has happened is this giant thing in the middle, which is a huge neural network, has essentially learned the statistical structure of human written language and all of the knowledge that is contained in the text that was provided to it. So if there is something about British English that is describing the way Beatles, did their first album, whatever that information might be, it has learned not only how Brits write their English, but it has also learned facts about the Beatles, right? And so on and so forth. Basically, this is what a language model is. It embodies the statistical structure of human written language based on text that we have produced and put out on the internet. And the reason why it's called large is essentially because it is large. These are giant things. And I was talking about training. Training these systems can take weeks, months, almost half a year sometimes, and at enormous cost and energy usage. But when all the training is done, what we have is something like Chat GPT. That is what Chat GPT is. It is basically a system that has been trained like this by just taking text off the internet, taking every sentence that is there, masking off the last word, and asking the network to learn how to predict that last word. And once it keeps doing that, for every sentence that's out there, you end up learning the statistical structure of human written language. And in this case, English, but it's done that for all of the languages for which there is written text. Just a brief history of how this has progressed. Large language models really kind of hit the scene in about 2018 when Google produced a model called BERT. It had 110 million parameters, and I want you to watch the way these numbers are growing, right? 2018, 110 million parameters. 2018, again, another company called OpenAI, which is the one that produced Chat GPT, came up with something called the Generative Pre-trained Transformer, which is what GPT stands for, and that had also about 117 million parameters. In a year later, GPT-2 came out, and it had grown to 1.5 billion parameters. And again, parameters, remember, these are those Ws, these are those knobs that you have to change in order to learn some pattern in the data, right? So 2020, GPT-3, and this is the precursor to Chat GPT, it had 175 billion parameters. And within no time at all, Google came up with a large language model called PaLM, and they're all trained in a similar fashion. They're basically taking text off the internet and presenting the text to these large language models and asking them to predict a word that has been masked off, and over again. Google's PaLM has 550 billion parameters, and then a few months later, Google announced Minerva, and there's a reason why I have mentioned this. I'll come to it in a minute. They fine-tuned, basically they took PaLM, which was just trained on text from the internet. It was not curated in any particular manner. It was just text from all over the place. And then they fine-tuned it, which means they trained it further on text that was specific to math, in the sense that the text had math equations in it. It wasn't being trained to do math. All they were doing was taking text that had math symbols in it and equations in them and doing the same thing. Here's a set of, technically they use different words, but let's say the math document had, 5,000 words, and you take 10 words at a time and ask the large language model to learn how to predict the 11th word, the 12th word, so on and so forth, right? So Minerva is important for our discussion. I'll come back to that. And then see how quickly things went. In November 2022, I remember I started writing a feature for Nature around this time, focusing on Minerva. And even as I was writing, the technology kept changing underneath. Before we knew it, Chat GPT was out there, and everything that I was researching and talking to researchers about was getting old. in a matter of weeks and not months. So Chat GPT comes out November 2022. It's based on Chat GPT 3.5, which has the same number of parameters as GPT-3, about 175 billion, but Chat GPT includes something called reinforcement learning, which takes human feedback in order to further improve the model. And again, we won't get into that, but if it comes up in Q&A, we can talk about it. And finally, in March 2023, OpenAI released GPT-4, and we don't even know how many billion parameters it has, which is kind of ironic. The name OpenAI, they started with this idea that everything about what they're going to be doing is going to be open. And, well, they have shut themselves down. Now, we have no idea how big this is. We don't know what kinds of data it has been trained on. We just have a general idea that it's pretty much been trained on the same way that all the others have been, but the specifics are missing. The previous papers had more specifics. Like if you look at the Palm paper, I'm sure Google will also follow suit now. Now that OpenAI is not revealing what it's doing, I think the others are going to start doing the same. So I think OpenAI really not open anymore. But, okay, so here's a very interesting thing that happened in the course of these things. So early 2021, GPT-3 fails badly on something called the math dataset. And the math dataset is a bunch of about 12,000 questions that are high school level mathematics, right? And to answer each question, you need to be able to reason. You need to be able to reason to some extent in order to produce their answer. And they were using GPT-3 to try and see if it could answer these questions. And you can't, I mean, these things have not been trained to answer any specific questions. All they do, and this is really important for us to, as consumers of this technology and as people who are probably going to be policymakers, etc., to really appreciate that all they do is given, let's say you present Chat GPT with 10 words, right? It then predicts the 11th most likely word to follow. And then it takes the 11th word and appends it to the 10 words that you gave it. Now it has 11 words, and it produces the 12th word. And then it takes the 12th word and appends it to the 11 words that it already had, produces the 13th word, and so on. So remember that question I showed you about theory of mind? Let's say that was 100 words long, right? ChatGPT didn't actually analyze that question. It just looked at those 100 words and said, what is the most likely 101st word I should produce? It produces that. It appends that to the 100 words. It has 101 words now, and it produces the most likely 102nd word. And it keeps going like this, right? And then it lops off your input and presents everything that it predicted. And the output that we saw, which all of you almost uniformly agreed that it was reasoning, that it had theory of mind, all of that was simply next word prediction, right? All it did, it did not actually read the question and understand what was happening in the way we think of what understanding means or what, right? I mean, this raises questions about what we do as humans too. So I think that's important to keep in mind. So this is what they were doing with with GPT-3. They presented a math question as text. Let's say the math question, in fact, I'll show you examples of it. The math question is just some bunch of text. Let's say another 50 words. All that GPT-3 does is take those 50 words, generate word number 51, 52, 53, 54 in sequence, and then at some point spits out whatever it has produced. And the question is, does whatever it has produced look like an answer to the question that you posed it, right? And in the case of this particular test that was done in early 2021, GPT-3 failed miserably. It was correct about 3.5% of the time, pretty much got all the answers wrong, right? So in July 2021, a company called Hypermind, based in California, asked experts in the field to make a prediction. They basically asked, on June 30, 2025, so remember this question is being asked in June 2021, so they're looking 4 years ahead and saying, what will be the state-of-art accuracy of a machine learning model on the math data set, right? So, and these were experts who were being asked. And the crowdsourced prediction was the best AI, and it doesn't have to be a large language model, any AI, they were basically saying it will be 73% accurate by 2025. This was an answer given in July 2021. And in July 2022, barely a year after that prediction was made, and the prediction was saying that it's still 4 years away, that kind of accuracy, Minerva, which I just mentioned to you, which is just a large language model called Palm, that has been further trained on math-specific text. But the training is the same. It doesn't understand math. It's just being asked to predict the next thing it sees. Based on input it sees, it predicts the next word, next token, as it's technically called. Minerva cracked 50% of the math data set. It got, all it's doing is producing the next sequence of words. And if you look at what it has produced, it technically qualifies as a solution to the problem that was presented to it. And I'll show you an example. It actually cracked 73% on the algebra-specific questions. So already it had reached something, the accuracy that these experts were thinking will take 4 more years, right? This was pretty amazing. And it really highlights, we may not have time to get into this, but this idea of fine-tuning pre-trained models. So when you just take random text from the internet, without really curating it, and train your model, you get something like, Palm or GPT-3, and then you fine-tune it with specific kinds of text. In the case of Minerva, it was math text. And that fine-tuning really changes how these things work. Okay, so here's a math example. Again, for some people, this will be really trivial. For others, it might feel like, why are we even looking at equations? But this is to make a point, right? So here's a question in the math data set. A line parallel to y is equal to 4x plus c passes through the coordinate 5, 10. What is the y coordinate of the point where this line crosses the y-axis? So you have to imagine this is the y-axis, this is the x-axis. There is some line that represents y is equal to 4x plus 6. I think I'm getting the actual intersections wrong, but so you're looking at the x-axis and y-axis. And the idea is there is another point 5, 10 through which another parallel line passes, and you have to figure out where that parallel line touches the y-axis, right? This is not a trivial problem. I mean, in the sense that even for an average high school student, this will take a little bit of thinking, right? And all that was done was this input was presented to Minerva, right? And Minerva looks at that, let's say that's 50 words, and it starts producing the 51st word, the 52nd word, the 53rd word, and so on and so on and so on, and out comes the answer, right? If you read this, we don't have to go into detail about this answer, but it is correct. If you read it, it looks like it has reasoned its way through the answer. But we now know that all it has done is it has just predicted the next word, given a certain set of words, appended the predicted word to what you gave it, produced the next word, and so on and so on and so on. And because it was trained with math symbols, it has the ability to produce math symbols, and you end up with an answer that looks like it has actually solved the problem by reasoning. But has it? That's the question, right? And if you just read this, right, just like when we just looked at the theory of mind answers, all of us thought it was reasoning, all of us thought that it had theory of mind. If you just read this, you'll say, yeah, it actually understands how to solve a math question, but has it really, right? And this becomes really interesting when you see when it gets things wrong, right? So another example is this interesting one. If the square root of 400 is equal to the square root of 81 plus square root of some number n, then what is the value of n, right? Fairly simple, straightforward problem. This is the answer that is there in the data set. This is not the answer produced by Chat GPT. This is already there in the data set, which Chat GPT doesn't look at, or in this case, Minerva, not Chat GPT. They're all the same at some level. So it's basically saying, the answer says that, we just make sure that we should not be fooled by the square roots. We can rewrite that equation by saying square root of 400 is 20, square root of 81 is 9. So 20 is equal to 9 plus square root of n. So n should be 20 minus 9 equal to 11. Or rather, square root of n should be 11. So n should be 121. The final answer we expect is 121, right? So this is what happened. Minerva was built using 3 different base models. One had 8 billion parameters. Another one had 62 billion parameters, and the biggest one had 540 billion parameters. Let's just look at the output of the 2 smaller ones. The 8 billion parameter model said, this is the answer that it produced. We have square root of 400 is equal to square root of 81 plus square root of n. Therefore, 400 is equal to 81 plus n. It basically removed the square roots, right? Which gives 300, which basically says n is equal to 319. And it says it confidently, the final answer is 319. This very clearly shows you that it hasn't understood anything, right? It just produces the next token in a sequence of tokens, and you end up with something that looks like an answer, but actually it's completely wrong. Except When the model got bigger, the same input was presented to that model. This is correct. It has done the same. The training regimen was the same. All that changed was that the model was bigger, right? And somehow its ability to predict the next token, in this case, ended up producing the correct answer. So the question is the bigger model now reasoning and the smaller one wasn't? These are questions. I don't have answers. I'm just posing this to everyone. This is something we have to think about. So what you witnessed here between the 8 billion parameter model and the 62 billion parameter model is a phenomenon called emergence, right? Where this seeming ability to reason, this apparent ability to have theory of mind, and I'm using the word seeming and apparent because that's how it seems to us from the outside. We don't quite know what exactly is happening within this, within these models, but they seem to have an ability to reason. We don't have time to get into this. Maybe again in the Q&A if we pick it up. If somebody has questions, and remember these words, chain of thought prompting or algorithmic prompting, but basically these are different kinds of abilities that the models demonstrate. And theory of mind, we saw in the output of Chat GPT that it had an apparent ability to model the mind of another. In this case, it was modeling what was happening in Alice's mind and was able to tell us what Alice might do or that she will have a headache the next day, right? So these abilities emerged in larger models. They were missing in the smaller models, even though the training, the way they were trained, the data that was used to train them was pretty much identical. It's just that the models got bigger, they were trained for longer, and maybe sometimes the data was curated a little better, but basically it has to do with scale. As you increase the training time, as you increase the number of parameters, as you increase the size of the data set, you end up with capabilities that seem to mimic reasoning or seem to mimic, in this case, I've just taken these examples, but these are all what can be called emergent properties. The real question is, are these things actually reasoning? So here's the same theory of mind question that I had posed to Chat GPT. The example that I showed you earlier was a question that I had posed to it a few months ago. Then as I was preparing for this talk, I took the same question that I showed you earlier in the first slide, posed the same question back to Chat GPT again. Look at what it says this time, right? Based on the given information, Alice initially places her reading glasses in the left side drawer. However, when she returns to the room and takes her glasses, she unknowingly takes the pair from the right side drawer, which have the wrong power. And then it basically says, because they have the wrong power, she will have a headache. But it got that wrong, right? So in this case, it's very clear that if you just read this and you didn't know what was expected, you would have no way of telling that it got it wrong. Except that because we have theory of mind, we can figure out what Alice should be doing. We know that it has got it wrong. But if this was a complicated little problem where you as a human didn't know what the answer should be, and you just read this output that came out from a large language model that looked so authoritative, and look at the language. It's the language grammatically and syntactically is perfect, right? So, but in this case, it got it wrong. So in one case, it got it right. In the other case, it got it wrong. And this is at the heart of what we need to be worried about with large language models. So let me just first briefly talk about the conceptual questions these large language models raise, and then we'll talk about what we should be concerned about. Have they memorized the data? How many of you think large language models are simply memorizing what's out there? A machine learning expert, 2 machine learning experts think that it's simply memorizing. This depends on the meaning of memorization, right? I presented it a theory of mind question that I really worked hard at making sure that it would not have seen that specific sequence of words in its training data, right? So that could be an argument, depending, again, I want to ask you during the Q&A as to why you think it had memorized it. Nobody else has picked up their hands saying it has memorized it. That's interesting. The experts are saying it has memorized it, and the others are kind of ambivalent, probably. I am of the persuasion that I think it is not simply memorizing. So here's a very good example. Today, if you go to the browser, let's say Google's Chrome or Microsoft's Bing, these large language models are connected to these browsers. Now, before these large language models, if you just wanted to do a search for a certain piece of information, you would go to Google and do the search. Google actually, in some very simple way of thinking about it, does a lookup. It kind of knows what your query relates to in terms of information that it already has. It has memorized the web, Google's previous version of the web search, right? So it somehow manages to index into a certain place in the huge mass of data it has and retrieves information that's particularly relevant to you. If you pose the same query to Chat GPT, it's not actually looking up anything. It's essentially doing, what it has learned is what's called a probability distribution over words. It's basically saying, given this set of words, what is the most likely next word? And then given those set of words, what's the most likely next word? It has learned a very, very high-dimensional complex probability distribution over all the words that it has seen. And that probability distribution embodies the syntactical and some would argue some amount of semantical structure of language. And we'll come to that in a little bit. There's not much more to go, but so when you look at it that way, it's not at all clear that what it's doing is actually memorizing. It's not factually, the fact that it gets things wrong, to me, is pretty clear indication that it hasn't memorized anything. Because, well, technically, it has understood the probability distribution of the data, right? And it has then to sample from it. And when it samples from that distribution, sometimes it gets it wrong, sometimes it gets it right. It's a stochastic process. So, this is an interesting question. And, the debate goes on about whether it has memorized it or not. Do they understand the meaning of the words they are generating? Now that you know what it's doing, forget the first responses that you had like about 40 minutes ago. Now do you think it understands the meaning of the words they're generating? Who says it's no? Everyone's nodding as if it's not understanding. So, okay. And I'm going to quibble with words here. It really depends on the meaning of the word meaning. And you can get 5 linguists in this room and ask them to define semantics and the meaning of meaning, and they will not agree, right? So depending on where you set the bar for what it means for you to have an understanding of a word, if you set the bar too low, ChatGPT clears it, no problem. If you set the bar really, really high as to what meaning should be, then it won't clear it, right? So this is again a debatable point. Are they actually reasoning? Again, now that we know how it works, it's easy to see that actually I don't see how it could be reasoning. But if you just look at the output and you had no idea what it was doing, we all raised our hands saying, oh yeah, it is reasoning, right? How are you so sure that we are not doing something similar as humans, right? We post hoc justify what we say as reasoning. I mean, yes, there are certain things we are very aware of having reason, but let's say theory of mind, right? Which is a completely perceptual thing. You don't have to do any specific conscious cognitive act to perceive somebody else's state of mind. It just arises in us as a perception. How do you know that that perception involves some kind of sophisticated reasoning, or whether it's just some kind of sophisticated pattern matching, not unlike what an LLM is doing? We don't know the answer to that. So are they actually reasoning? Really, again, there are no black and white answers here. I'm just posing these as questions that you have to be thinking about when you, and this has certainly ignited a debate among linguists about the nature of language itself. This is very fascinating, and if you're interested, you should go look at what's happening, in the community of linguists who had for decades been working on understanding language, and along comes this weird thing called a large language model and turns their world upside down, and they're trying to figure out what it tells them about language itself. And it raises questions about intelligence versus knowledge. What is the connection between intelligence and just knowledge? And again, these are not clear black and white boundaries. The answers are not very clear. These are the questions that the arrival of large language models have raised. These are debates that are happening in the field. I don't have any answers for you here. For us as consumers of this technology, the really important part is to worry about these things. So you will often hear the phrase that these large language models can hallucinate. So when they produce wrong answers, the phrase that's used to describe what they're doing is, oh, they're just hallucinating and coming up with wrong answers. But actually the process that generates the right answers is exactly the same. The process that generates the wrong answers is exactly the same. If generating the wrong answers is hallucination, then producing the right answer is also a kind of hallucination, because in terms of what is happening with the mathematics, it's exactly the same inside the model. right? So the fact that sometimes the answer looks wrong because we know what the answer should be, and we call it a hallucination, is kind of weird, because it's always hallucinating or it's not, right? And I would say it's always hallucinating. And again, if you go back to neuroscience and start looking at sort of questions about our own perceptual processes, neuroscientists use the same word, that we are constantly hallucinating, right? And usually our hallucinations are in accordance with physical reality, so we don't have any problems. But if some of you have ever ingested a substance and you start hallucinating, that hallucination is not in tune with physical reality outside. And we call that an hallucination. But the processes inside the brain are exactly the same whether the hallucination is in tune with physical reality or not. Something similar is happening here, right? So the other thing is, if the training data is not curated, or if the outputs are not filtered, then the LLMs, these large language models, have learned all of the nasty things that we as humans have put out on the internet. There's sexist language, there's racist language. There's so much hate speech, and all of that stuff is now inside these LLMs, right? So they can, if you didn't put any checks and balances on them, they're very, very capable, and it has been shown over and over again that they will produce exactly those kinds of outputs. And most importantly for us, by definition, they're confident of their output, right? So they make false statements with utmost authority, right? There is nothing in the output that they produce, at least the current LLMs, which suggests that they're not very sure, but it doesn't tell you, oh, I'm 55% sure. It basically says this is the answer, right? And actually, when it's trying to predict the next word, it might say, let's say it has a choice of 2 words that it should produce next. One is 52% likely and the other is 48% likely. It'll pick the one that's 52 and say, okay, that's the next word. It doesn't tell you that the difference between one and the other was just 4%, right? So, and eventually it produces an output that looks as if it's completely sure of what it's producing. We were able to pick up on the errors because we knew what the output should have been, because we could analyze the output. But there will come a time, and it's already happening, where humans don't have the expertise to analyze the outputs of LLMs, and we are not able to tell whether it's producing fact or fiction, just making stuff up, right? So this is a real concern. And so basically, what are the real pressing concerns that we should be thinking about as people who are concerned about this technology? It is honestly a very, very disruptive technology that potentially could cause short-term job losses. And Jan and I were talking about this the other day, and we kind of agreed that short-term disruptions are very likely. In the long term, it's unclear. Maybe humanity will achieve some equilibrium with these LLMs, and we'll figure out how to retrain ourselves in order to function better with these things. That is unclear. If we don't put checks and balances on the training data in terms of what biases exist in the training data, and if we don't put checks and balances on what these things produce, then existing biases in society will get entrenched in these large language models. And if we are going to use these large language models then to dictate how we do things in society, then those biases are going to get further more and more, right? So we really have to watch for it. And of course, this is already a problem. Generating propaganda and misinformation well before large language models came onto the scene was already an issue. These things have made it so much easier to automate that process, and so much easier to generate text that looks grammatically correct and is really hard to tell, what's coming out of an LLM anymore. Again, there are people working on trying to figure out when a piece of text is coming from an LLM versus when it's not. But it's a race. There's another race going on there where. So anyway, so these are things we should be concerned about. Quickly, 2 more slides. I just want to give you a sense of scale here. So LLMs that we were talking about had 500 billion, let's say, connections or the weights. Let's say it has 1 trillion. The biggest large language model right now has 1 trillion connections. To put this in context, the human brain has 86 billion neurons and 100 trillion connections. And these connections are we're just talking of connections between neurons, right? So already, if you're just thinking of connections between biological neurons and the largest LLM, there are 2 orders of magnitude. Magnitude apart. So 1 trillion on the artificial side and 100 trillion on the biological side. But this biological side doesn't take into account that the communication between neurons is not simply to do with the connections and the strength of the connections between the neurons, but there's this complexity associated with neurotransmitters and the fact that the dendrites, those things that come in and provide information to the neurons, they are themselves doing computations. There are extracellular cells like glial cells that are involved in the way neurons can communicate with each. So there's a lot of stuff happening. So this 100 trillion is probably a very serious underestimate. So this actual number, if you just want to think in terms of connections with, large language models have 1 trillion, how much does the human brain has? It probably has way more than 100 trillion equivalent connections. What this means is that already with 1 trillion connections in the artificial system, we are seeing behavior and properties that are astounding, both amazing and inspiring, and also extremely scary and problematic, right? Now imagine if technology were to scale the artificial system to the size of a human brain. So we got to the size of 100 trillion or 1,000 trillion connections, right? Then you have a system that has the capacity of biological brains, but also has access to information that no single biological brain has access to. You or I will never know what's there on all of the internet. An LLM does, right? So you take the processing capacity of a biological system, build that into an artificial system, but then give it access to all of this information, and you give it the speed of silicon. Our brains are not as fast as silicon. And you couple all that, and you just have to imagine where this is going, right? And I think, to me, it's, again, both amazing what's happening and also really something that we should all be waking up to and, kind of get to grips with the fact that this is a disruptive technology and it will really influence our lives in the next 5, 10, 15 years quite a lot. So I just want to end with this quote. Well, this is a quote thanks to Peter, who alerted me to this wonderful quote that just fits very aptly. So, about the future, actually the situation is hopeless but not serious. I have no idea what that means, but it sounds perfect for this. This is a German actor in Billy Wilder's movie called 1, 2, 3, and Peter recommends it very strongly. So thank you. That's all I have, and we can take questions now.